Well, thanks Chris, and thanks everyone for coming today. Yes, these are some examples of the multispectral maps I'm going to be talking to you about today. These are really interesting. I mean, it's a world first. It's really great for Australia to be the first country to produce this kind of mineral group map of a whole continent, and really great for GA to be a part of this. But interestingly, although these maps were designed and funded largely by the resources sector, there are a lot more applications. They're national data sets, there's 17 different mineral group products, there's a whole range of things from soil and environment mapping, hazard mapping, all sorts of things, and I hope a few people here might be able to see some applications for their own work. I think even you could say the best application for these maps is yet to be discovered. But first, I've got something for you to think about. You may have seen it before. It's the surface geology 1 to 1 million map of Australia. So I'd just like you to think about, how are these maps made? Something we can all be proud of. Decades of work by many geologists doing years of field mapping, looking at aerial photographs. But something I'd like you to think about is, how were they made? So the geologists making visual observations, aerial photo, they're also using visible light. And I just wonder, is there anything else? Is there something beyond that? Is there something we're missing out on? So I guess I'd like to propose that using a new technology, we're really getting a new way of seeing, an ability to see the continent in a new light. So I'd like to talk about what spectral geology and tools like ASTER satellite data can bring to us. So using wavelengths beyond the visible light range, we can actually see mineralogy, not just the usual orange, red, grey, brown that we normally see most rocks appear as, but in terms of iron oxide, silica content, clay chemistry and that sort of thing. So here's the Landsat red, green, blue composite image of Australia. You can see the vegetation all around the coastline in green. You can see the usual shades of orange and yellow that most of the surface appears as in the visible light range. Now what I'm showing you is one of the new ASTER mineral map products. This is the iron oxide content map of Australia, and this is using some shortwave infrared light to look at the continent. So this is really giving us something beyond the visible light. It's almost like we're seeing with a new set of eyes. Another example, this is an iron oxide composition map. So you can see down here on the legend, we've got the goethite rich in the blues, going up through the greens into the warmer colours, the yellows and reds which are more hematite rich. And this is actually showing iron oxide composition across the whole of the continent. Again, this is some of the shortwave infrared light. Just a brief overview of what I'll be talking about. I've nearly finished the introduction, so I'll go into a bit about the project background and the collaborators, some technical and spectral theory, a bit about the range of applications of these maps. I've got 3 case studies to show you, and also a bit about future spectral geology applications and data integration. So it's quite a large project led by CSIRO, Dr. Tom Cudahy, the Director for 3D Mineral Mapping over in CSIRO, as well as GA and all the state and territory surveys. So really great to have all the states working together with GA and CSIRO on this, but also some key internationals who made the project possible. So particularly Japan Space Systems, formerly known as USDAC, the USGS you'd be familiar with, and NASA's JPL. So what is ASTER? Well, it stands for the Advanced Spaceborne Thermal Emission Radiometer. That's a picture of the satellite platform there. It's really the first and still the only geoscience-tuned satellite sensor that we have at the moment. It's multispectral, which means it's got 14 bands. It was designed and built by the Japanese, but launched on the US Terra satellite platform in December 1999. So we've got over 10 years worth of data collected by this instrument. There are some instrument issues, I'll go into those a bit later, and you can still get the raw data available from JSS. So that's the actual satellite and instruments before launch. You can see that it's quite an impressive collection of foils and so forth. Looks like something out of a 70s sci-fi TV series. But basically what we get from this instrument is a 60 by 60 kilometre scene size. We've got 14 different bands, which you can see down here. This is the visible to near infrared range, where we have 3 bands. These have a 15 metre pixel resolution similar to Landsat. Importantly, we've got this shortwave infrared region where there's a lot of important geological information at a 30 metre pixel, and then ASTER also has 5 bands in the thermal infrared range up here with a 90 metre pixel. So this work really started around 2006 when the PMDCRC released an initial Mount Isa super mosaic. That was about 30 ASTER scenes. That was the largest mosaic of its kind at that time, made by Simon Oliver and Simon van der Wielen here at GA. And about that time, CSIRO also developed its CSAT map software and started development and testing a standard methodology and product development. From around 2008, CSIRO negotiated with Japan and NASA to access the complete ASTER archive over Australia, that's over 30,000 scenes, and started developing state mosaics and products, which were delivered from about 2011, culminating, as Chris mentioned, in the All of Australia ASTER project, the public launch at the IGC in Brisbane in August last year. And since then, we've had 9 very successful industry workshops that have been really well attended, lots of conference presentations. We've had 2 graduate projects here at GA, hundreds of data downloads, interestingly in over 30 countries, which is pretty amazing for an Australian data set to get so much international interest, and at least 1 new mineral discovery, which I'll talk about later. And the team was awarded the Australian Explorer of the Year for 2012 by Australian Mining magazine. So once these scenes were collected, we had to go through the 30,000 scenes. Here's an example of a collection of all the scenes for an area. You can see these white scenes have lots of cloud overlapping by some with a lot of vegetation. This is the false colour image, so the vegetation appears red. And so what we'd do is go through, get rid of any really cloudy scenes, any scenes with a lot of green vegetation, try to get the scenes with the best geological information. So out of the 30,000 scenes, we ended up with a subset of about 3,500 scenes to make the mosaic of Australia. These are then subset and mosaiced and calibrated and undergo various stages of processing and validation. So what you can see here is the version 1 of the National ASTER mosaic. That's the false colour RGB composite there. These pink dots all over it are actually the ASTER scene centres. So you can see all the ASTER scenes and where they occur across Australia. So we have a pretty good, nearly 3 times complete coverage of Australia. These little yellow strips you can see going through here, this is another kind of satellite sensor. This was the Hyperion satellite. It was a higher spatial and spectral resolution satellite, but just a test satellite, and you can see it doesn't have very extensive coverage, just quite patchy coverage across the continent. This data set was really useful though as a calibration tool. The Hyperion satellite is higher spatial and spectral resolution and has been very stable over time. Unfortunately, the ASTER instrument has not been so stable. The short-wave infrared module suffers from some crosstalk problems and in fact ceased functioning in about 2009. But what we were able to do is where there were overlapping pixels between the Hyperion and the ASTER mosaic is we generated a set of gains and offsets to sort of correct or improve and validate the ASTER mosaic with. So there are issues. I guess one of the things about this data set is we were able to access it for free. We're able to provide these 17 mineral group products for free, but it does come with a few issues. There are instrument effects, there's some noise, some calibration issues. Some of these we can correct for to a certain extent. Things like cloud, where we were unable to obtain a cloud-free image, we could make a cloud mask and mask out the bright cloud tops and the cloud shadows. Things like green vegetation we can also mask, and a lot of the products have had a cloud and green vegetation mask applied, which means those pixels are just removed out of the data set and appear as black or blank. Things like dry vegetation, which is quite extensive in a lot of parts of Australia, are a bit more difficult to deal with. They have a lot of crossovers with the geological information, and if we removed all the dry vegetation, we'd be removing too much of our geological information. So there are still some issues, and we do provide a set of product notes that go with each of the products to describe these in some detail. But the version 1 of the Geoscience Maps, as I said, is 17 GIS compatible mosaics. We've got these 30-metre VNIR and SWIR products, which I've listed here. You can see there's a couple of RGBs. We've got the false colour composite, which I showed you before. There's another one called a regolith ratio product. And most of these other products, such as the ferric oxide content, ALOH group content, these show abundance or content at the surface, and they'll be from low to high abundance. There are 3 products, however, which map chemistry. These are called the composition products, and I'll show you an example of those in a moment. There's also the 90-metre thermal products. We've got silica, quartz and gypsum, and these are also abundance products. So here's an example of the thermal products. This is the silica index or content map for Australia. You can see this and the ferric oxide content, which I also showed you before, show abundance, so from low to high content across the continent. And this is an example of one of the composition maps where we're looking at ALOH composition. So we're actually going from well-ordered kaolins, aluminium-rich muscovite zeolites, etc. in the purples and blues, going up through into the more aluminium-poor, silica-rich muscovites, fengites, etc. in the warmer colours here. So now a bit about the technical background and spectral theory. Well, if this comic that I found on the internet is anything to go by, the superhero Spectra spends most of her time battling the evil and blue head misalignment, which certainly sounds familiar. But, you know, what's with all these squiggly lines? What do they mean? Well, really, we're talking about a physical property, the reflection and absorption and emission of light, or electromagnetic radiation. So here's the electromagnetic spectrum. There's an enlarged section here. This is the part you're all familiar with. This is what you can see. It's visible light, so going through purple, greens, yellows, about 400 to 700 nanometres, and that's just this part of the spectrum here. This is the area that ASTER is sensitive to, so it goes into the infrared, and also the thermal bands are located up here between the microwaves and radio waves. So with a passive system like this, like a lot of satellites, we use the sun as our source of radiation, and what happens is the electromagnetic radiation from the sun hits the surface target, it's refracted, reflected, some of it's absorbed, and the sensor collects a returning signal. So what we have is the response hitting the target, and depending on what that surface is made of, depending on the structure of the minerals, we get a spectral feature, a spectral absorption, and this is what tells us about the composition. What this actually reflects is how light is bounced around inside the crystal lattice. You're really mapping things like small cation substitutions in the crystal lattice from space. It's a pretty amazing thing to be able to do. So here's an example, a bunch of the squiggly lines. The one at the top is a dry vegetation spectra. In red we've got a sandstone, I've got a limestone, under that in blue there's a dark soil, and cross-cutting through those, this green spectra is a green vegetation. And so I'll just explain a bit about these different areas. This is the visible to near infrared wavelength region, and as you can see this is important for the vegetation. There's quite a pronounced absorption there for the vegetation in that region, but it also covers things like iron oxides, rare earth elements. Moving across into the shortwave infrared, which as I said before is a really important part where a lot of mineralogical information that we're interested in is contained. So you get things like your OH bearing minerals as well as some information you can see here in the carbonates. And then going up into the thermal infrared, the thermal where you have your non-OH bearing silicates, and again you can also see a bit of information about things like carbonates. Just to give you an idea of some of the different sensors, there's a couple of the hyperspectral sensors at the top here. Hyperspectral just meaning many tens of bands, often hundreds to thousands of bands. So we've got a couple up here. You can see HIMAP, which is an airborne instrument you might be familiar with, has about 126 bands. and that's compared to the multispectral instruments like ASTER and Landsat. The key difference between them being that ASTER has many more bands in the shortwave infrared, which is one of our important regions, and if we zoom in on that and think about the difference between what we call the spectral resolution, you can see this top spectra is a really detailed laboratory quality spectra. What we're looking at is an absorption feature with a nice asymmetric shoulder here, and that's quite diagnostic of an individual mineral species. Then going to something a bit coarser like a high map, you can still resolve the depth and shape of that feature, just not quite as nicely as the laboratory one. Whereas with ASTER, you kind of can get that there's an absorption feature there, but you just can't get the individual mineral species, and that's why the ASTER map products are just mineral groups. They're not individual minerals the way you could get with a high map product. You can see the problems you have in resolving some of this detail just with the one band you have in the Landsat. So there's a range of applications. I mean, as I've said, certainly a lot of applications in mining and exploration, but really this is a spectral technique that just can quantify the surface mineralogy. So you're mapping all the materials at the surface. Sometimes, unfortunately, that includes vegetation. The environmental mappers don't mind that too much. They, in fact, like that information. But you just have to keep in mind that this technique has about a 5 micron penetration. It's really just the very surface. However, we can use that information to understand and map things like the regolith character and thickness. You can also use different mineral group maps to understand your rock types. Things like being able to check and use mineralogical tools to look at old geology maps or to test and inform your geological models. There's certainly applications in alteration and mineral systems footprints, and I'll talk a bit more about that. It being a new tool for explorers even in known bedrock regions, and I'll explain that in the Jervois case study a bit later on. But a lot of you here would be familiar with the surface geology and the term the sea of yellow, and how can the explorers get around this cover that is obscuring the wonderful bedrock geology. Well, a few things that we can use ASTER for is things like looking through the cover to see if we can find windows of bedrock. Interpreting the cover origins can be really important, so looking at transported versus in situ materials, estimating cover thickness, finding redox zones, basically understanding the landscape that the explorers are exploring in. So there's a whole lot of things that explorers want to find out about to understand the environments that they're exploring in. Things like, is this sediment or material transported or in situ? Where are the redox boundaries? What's happening with the pH? Where's the water table? And there's a whole lot of mineralogy tools that we can use to understand these. So just a brief introduction to regolith mineralogy. The main point I just want to make here is that we start with fresh rock, which as you start to chemically and physically weather that, you go up through into saprolite, into a modelled zone, and of course the final result is you end up with a high level of chemical and physical weathering and either loose piezolyths or soils, etc. at the surface. So as you go up through this weathering process, you have decreasing primary minerals as you go along. Your clay chemistry changes, your kaolin crystallinity decreases as you go towards the surface, and things like what's happening in the iron oxide profiles, your iron oxide chemistry. Here's just a simplified landscape model. There's some of the different components that you might be interested in mapping. And then this is some of the mineralogy. What are the minerals that you'd look for to identify whereabouts you were in that part of the landscape? So I'll just go back again. We've got things like a felsic rock or a mafic rock, and some breakaways and some lateritic lags. And then you might be looking at things like your white micas or chlorites, iron oxides at the surface and things like that. So here's an example from South Australia. This is the northern tip of the Flinders Ranges. You can see some of the beautiful folds and shapes in the exposed bedrock of the ranges through here. This is the actual range front, and this is the ASTER silica abundance map. And so what we're seeing is all these enormous colluvial and alluvial fans shedding material off the side of the range front. And what's really interesting about this is in the visible light, this all just looks like sand and colluvial material. You can see these very fine lines over here in the east are all linear sand dune fields. But what this product is showing is some very interesting differences in the silica content. So the toe of this colluvial fan seems to be really enriched in silica. That's very interesting. For people like uranium explorers, they want to know about evaporitic things. Is this an interaction of the groundwater with the surface or with the fan? Is it a redox boundary? What is this? So this is really giving us a way to differentiate or divide up parts of the landscape and see some interesting features that we would be able to then go and check out in the field. So here's the silica image for the whole of Australia, and it's quite interesting that it correlates very well with the sandy deserts of Australia. So that's the high quartz sand content in the yellows and orange and reds, and that's the location. I'll just show you. It's a figure from the GA book, a figure by Payne et al., which shows you the sandy deserts across Australia. And I'll just go back to show you the silica image. So I hope some of you are interested in looking at these maps. The project has made these maps available in a number of ways. People, of course, can contact me if they want internal access, but for our external clients, we've got the sort of old school way where you can get a hard drive from the sales centre. We also have online delivery through the Auscope portal where people can click a box and just do a cookie cutter version of which data sets they'd like to get in different areas. But our most popular delivery tool has been the NASA Whirlwind Viewer, developed by Michael Hoog and Hoog and GA's 3D Viz team. And this is a really fantastic tool. For those of you who aren't familiar with it, it's basically like Google Earth, but with all our great national data sets. You can pull in all your other data sets, and it also has all these ASTER products that Michael put in there for us. It's really, really fast. It's a really easy way to view the products. Here's an example of what the Whirlwind Viewer looks like. You can go to this link to access it, and you can add in down here at the data sets. There's a whole bunch of GA's data already in here. Here are the ASTER products. You can click on which products you'd like to show and then turn them on up here. We've got the ferric oxide content. This is some really spectacular channel country somewhere in southern Queensland. And also you'll see, I don't know if you can see, it's quite faint, but there's a little information button which provides some quite detailed comments on each of the products, how they were made, some of the applications that we recommend, and some caveats about instrument issues or effects from vegetation mixing, etc. So I'll go into the case studies. I've got 3 case studies or some examples of how to use the products. First, we've got Lake Barlee in southwestern Western Australia, where we've been looking at some salt lake mapping. Then we'll go to the Pilbara, also in Western Australia, but further north. And then finally a trip to the Northern Territory, where we'll go to Jervois and look at the high-grade greenfields discovery there. But first, Lake Barlee. So this was part of work done by GA for a mineral assessment for a salt lakes project at GA, where they wanted to do a first pass assessment of the types of salt lakes around Australia. So we're just zooming in on this area here. It's a pretty big salt lake, which is a good example. You can see that's a 30-kilometre scale bar there. What can you see in the Landsat? Well, it's sort of this grey, evaporative looking thing. Maybe there's a bit of salt. It is a salt lake. Is it salt or gypsum? Don't know. There's a bunch of vegetation around and probably a few sand dunes, although you can't really see them so well. But what can we see in the ASTER? Well, this is the silica product, and this shows really nicely some of the aeolian dunes. You can see the dunes around the perimeter of the lake. You can see them longitudinal dunes traversing into the lake a little bit, and it's a really clear picture of the coarse quartz sand content making up a lot of those alluvial materials. Also in the thermal we have this gypsum product, which is pretty amazing. It's not masked. The gypsum all over Australia really only occurs in a few of the salt lakes and just in a few areas, and traditionally this kind of work would take a lot of hours doing surface sampling. It's quite difficult to get out to these salt lakes and then to get to all these different parts of the salt lake. So it's pretty amazing that we can sit at our computers, not have to leave our desks, and we can actually look at the gypsum content across some of these lakes all around Australia. Another interesting product, we haven't yet been able to ground truth this, but this is the opaques product. This is an interesting product which really is just mapping out dark materials. It includes things like carbon black or ash. It can include dark, just any sort of dark materials. And here it could be, if you look at the gypsum map, it appears to be the inverse of the gypsum map. So it's probably something like an organic rich mud or sediment that's occurring in some parts of the lake where the gypsum isn't covering it. And then we'll go to the Pilbara. We're looking at channel iron deposits. This is an area where there's a lot of iron ore mining, very valuable to Australia. So we're going to go to the Rockley Dome. You can see the coast of WA just here, and we're going to zoom in here on this dome structure. So this is the ASTER iron oxide product. And we're just zooming in. This is the Rockley Dome, and you can see quite well this iron oxide product is picking out this channel which cross-cuts across the landscape. And this is what the mining company's targeting, and they want to know where it goes undercover and what happens to it. And the original geological mapping maps out the channel as going, if you can see the dotted lines through here, but we can see quite clearly in this iron oxide product that it probably actually goes undercover here, and there's a bit more up here. So that's important for mining companies to be able to fine-tune their resources and see extra things like that they might have missed. And then our third case study, going to be talking about alteration mapping. So we're going to go to Jervois in the Northern Territory. So here we are, there's Alice Springs, and then we're about 350 kilometres northeast. This is the Jervois prospect out on the Plenty Highway. So most of these we're looking at strata brown copper deposits. The company here used to be called Kentor Gold, is now called KGL. They have the tenement. They've got about 12 kilometres of prospective strike along here. The basic geology, we've got some Georgina Basin sediments in this buff colour up here, and then we've got a range of schists. We've got a quartz sericite schist in the red here. We've got some magnetite, quartz chlorite schists, and this is their lode sequence in the pale blue. So you might have heard of some of these deposits. We've got Reward and Marshall, and also Bellbird down here in the south. So when we're releasing the Northern Territory ASTER map, we had a workshop in Alice Springs, which a lot of the company guys came to learn about the products, and we asked Kentor or KGL if we could use their tenement as an example since it was near the area. We weren't familiar with the geology, but we thought they might like to have a local example. They said sure. And so my colleague, Karsten Laukamp from CSIRO, put together this diagram where we were trying to show the industry guys how they could use, say here we've got the MgOH content, how they could use it to map that and understand their geology. So Karsten was saying, oh, you can see the carbonates show up in this product in these sorts of blues and green colours. And then have we got some, chlorite and biotite alteration around here? And the company guy said, no, you haven't. There's no alteration in those areas. There's nothing like that out there. And Karsten and I were a bit worried about this, and we said, are you sure? And they said, yeah, they're the local geos. We didn't want to argue, but we said, have you actually been there? And they said, oh, that's not a prospective area. And we said, would you mind checking, because we're a bit concerned that we were so sure that we were seeing some alteration, and the company guys were so sure there wasn't any. So they went out and checked it and did some surface sampling. Here's some of the copper results that they got from around this area. So there's some quite high copper. They also found in some parts 50 to 56 grams per tonne gold in quartz veins. And so this was possibly a new style of hydrothermal mineralisation in the area. So they were pretty excited. We were pretty excited. It was good to know that we weren't seeing things. So they actually declared this a new high-grade gold prospect called the Chubco prospect, and they've started a comprehensive sampling and mapping program, and I think their first drill holes plan to go in November this year. So that's a really good success story. What are some of the regional implications we can get from this? Well, this is the Bellbird and Reward area, so Kentor's tenement down here that you can probably just see the red spots from the alteration. This is more of the Georgina Basin sediments. So these other areas out here, are these more prospective areas? We don't know. We ran another workshop in Alice Springs about 12 months later. We asked the company guys if we could use any of their areas as examples again, and they said no, we'd rather you didn't. So I guess it's good that they value this information now and want to keep it to themselves. They've said it's something that they're really using as part of the exploration targeting now. So that's great. And there's one of the stock exchange reports saying that they're going to start drilling out there. So in summary, the ASTER data is a lower spatial and spectral resolution than some of the hyperspectral products such as the airborne HiMAP, but these products are free. We were able to acquire the whole data set over Australia and provide mineral map products online to everyone. We've calibrated it as best we can. We've tried to do things like the cloud masking and vegetation masking to improve the usability of the products and also improve the accuracy. They've been delivered in a way that is easy to integrate with other data in the GIS, but really the viewer is such a fantastic fast tool, the way you can zoom in and out and turn on all different data sets very quickly and easily. It's been incredibly popular. So I've gone through a few of the applications, so certainly mineral exploration, both covered and exposed terrains. It's great for alteration mapping and your regolith characterisation and mapping. I think there are a lot of applications for regional soil chemistry, and I'll talk a bit more about that later, and of course environmental and agricultural applications as well. But I'll go into a bit about the future of spectral geological applications, some other instruments, and a bit about data integration. Well, one of the projects GA is looking to do soon, another collaborative project with CSIRO, and that's using the National Geochemical Survey of Australia database. So some of you might have heard Patrice de Caratat present on this before. This is one of our national baseline chemistry data sets. What's been done is, if you can see these pale grey lines, the whole of Australia has been divided up into catchments or sort of super catchments, and for each catchment a surface sample has been collected. In fact, a surface sample and then about 50 centimetres below that sample. So we've got a top and a bottom of hole sample. So 2 samples for each catchment across the whole of the continent. They haven't finished collecting it all yet, so there's a gap here, but you can see all these sample points. This is showing soil pH for Australia. And this is something where we have this fantastic chemistry data set, and we're saying, can we scan these samples with high resolution lab spectrometers and get a matching spectral data set which will give us mineralogy. So we've got a sort of chemistry data set and then a potential mineral data set to go with that. And one of the reasons why we think, you might say, oh, how can a point data set relate to a 30 or 90 metre remote sensing data set? And I think one of the reasons why, and you can see here's the ASTER ALOH or clay composition map of Australia, and it has the NGSA geochemistry samples for soil pH. And we think one of the reasons why there's a good correlation between these data sets is that the ASTER data has a 30 to 90 metre pixel, and the NGSA samples, although they're point samples, they were designed to be overbank deposits. They were designed to be something that would be as representative as possible of that whole catchment. So it's actually quite a good potential match there. Here we've got the ASTER silica map. You can see that we've also coloured up the NGSA sample points. We've got the silica content from the NGSA results there. And there's a pretty good correlation there. You can see of course, around the coastline, the ASTER products have had a vegetation mask applied because they're very green, so most of these pixels are actually missing in the ASTER data set. So that's the main area of discrepancy. You can see in these other areas there's pretty good correlations between the silica content in those two different data sets. So that's something that would be a great data set to have. Information like this can also be used with things like the higher resolution HIMAP that I mentioned before. So this was an Australian designed and built hyperspectral sensor. It's got about 126 bands. This is the HIMAP instrument down here. It'll actually fit into any plane with a standard camera port. And yeah, that's another kind of enhanced data set. Also, another hyperspectral tool we have is for core logging. So this is sort of at the smaller scale. There's the instrument called the HiLogger, which is now in most of the state and territory surveys. And it's basically a heavy-duty spectral scanner. It also collects a high-resolution image of your core. There's a smaller version called HiChips, which does chip trays. And there's also the thermal logger, which has now been incorporated as part of all the HiLoggers, which increases the HiLogger wavelength into the thermal. So originally it had just been shortwave infrared, but now also has the thermal bands added in, which is great for things like comparing to the ASTER data, which also has some thermal products. And so what can we do with this? Well, once we start looking at things like HiLogger data, you can go into the 3D, you can use your ASTER and your HiMap for a surface layer, and then you can get your 3D spectral information. So here's an example by Carl Young from Barrick Gold, where he's modelled the gold envelope in grey here, and it's a little bit hard to see the blue on black, but the blues and greens through here are all the high-logged holes that they have through this area. And so they're particularly interested in this area and focusing on the mica composition and the mica chemistry. So they've plotted all their holes, and this means he's able to actually generate slices through there of mineralogy and the intersection and how that relates to the gold. So this is just one of the examples of how incredibly powerful this can start to be when you look at data integration and combining several sorts of data sets. When I was at the Geophysics conference, the ASEG down in Melbourne just a few weeks ago, a student from Codes, a guy called Matt Cracknell who's doing a PhD, came up to me to show me this very interesting map that he'd been making, sort of as a bit of a side project, but he just wanted to show it to me, because what he's basically done here is take a whole lot of GA's national data sets and put them all together. I'm not an expert on self-organised maps, but I think it's a kind of unsupervised classification where you can take in a whole lot of quite different data sets and sort of stack them, and the computer is able to make its own groups based on similarities or things that it finds coherent sets of attributes for groups across large areas. And what's really interesting here is the data sets that he's put in are quite a few of our geophysical data sets, so gravity and magnetics. He's also used a few surface sets, so he's used the radiometrics, and those holes you can see are from the radiometrics data sets largely. So the surface ones, he's got a radiometrics, some topography, and several of the ASTER products. So I think, wow, you know, what are we going to get if we start combining some geophysical products with some of these surface mineral maps? You know, can it make any sense? What will we get? Well, it's pretty interesting to see a map like this, which has so much apparently lithological sense coming out of a combination of such different products. And I think this really shows part of the idea that we don't even know what the best use is for this data sets. It's things like this that people will really be able to try to tease out interesting things by integrating all sorts of data sets at once. So going back to the Landsat image of Australia, and it's looking a little bit plain now, just those oranges and yellows, because really we know there's a whole lot more there. So I hope that I've been able to show you how much these new satellite ASTER Geoscience Maps, it's like getting a new set of eyes, and I hope that it can help you to assist your geological understanding. And of course, I'll put on some important acknowledgements for all the various people who've been involved in this project and the material for this presentation. I do have a few of the Whirlwind CDs here if anyone would like one, and I might just leave up Matt's really interesting map, and I'd be happy to take any questions or comments if you have any.